we have question 5A, and this is 2023. So they say, state the name of the logic gate represented by the symbol in figure 7. Figure 7, this would be a NAND gate. Now, this table here is a very important table to note, um, to have in your notes. So you have the AND gate, the symbol for the AND gate, the circuit symbol for NAND, or no and not. Based on the symbols here, this figure 7 would be a NAND gate, right? A NAND gate. This is the name of the logic gate using the truth table shown in the table below. So you have two inputs and an output. The output is the opposite of the input. So if the input is 0, the output is 1. If the input is 1, the output is 0. So based on that, this would be a NOT gate. So when the input is 0, the output is 1, and when the input is 1, the output is 0. This gate simply switches the logic gate, right? This is the NOT gate. So putting, this is the name of the logic gate. This is a NOT gate. Understand this, right? Now part 3, this is the tricky part. Let's say figure 8 is a digital circuit consisting of a combination of basic logic gates. So first of all, you need to know what type of logic gate you're dealing with for part C. Part C, if you look here, that looks more like an OR gate. So I'll put OR there. Part D, this looks like a NOT gate, right? Based on the symbols here. Triangle with a circle at the top. E looks like a NAND gate, because they have the little circle on top. So this is a NAND. And Z is our OR gate as well. So the input for A and B would be, the first one will be when both are 0. The second option will be when A is 0, B will be 1. The third one will be when A is 1, B will be 0. And the last combination will be when A is 1, B is 1. So for C, which is our OR gate, we look at the truth table here. I mean, well, you gotta memorize this, right? But I'm using this to explain the solution. So for the OR gate, this is the OR gate here. When you have the input, the two inputs are 0, you get an output of 0, everything else is 1. So we look for when we have two zeros, and we put a 0, and everything else becomes 1, because they don't have another combination of two zero, right? Um, so that's why you filled out part C. Part D is a NOT. So you look over here, the gate simply switches the logic state. So part D, remember the input for part D is B, right? Um, the input for C was B and A. So for part D, the input is just B. So it can just be the opposite of what is B. So if B is 0, here will be 1. If B is 1, here will be 0. If B is 0, here will be 1. And if B is 1, here will be 0. E is a NAND gate. So for the NAND gate here, when you have a 1 and a 1, you get a 0. Everything else becomes 1. So you look for a 1 and a 1. What are the inputs here? The input is D and C. So looking at C and D, when you have a 1 and a 1, it becomes 0, and everything else is 1. So here is 1, 1, and 1. Right? Only a on and a on is a off. Everything else is on. One, considering that 1 is a on. Now Z is a OR gate. And we just learned for OR gate, when you have two zero, you get a zero, everything else is one. That is for the OR gate, right? What are the inputs for Zeno? Well, for the OR gate there. E and C. So we're looking at E and C. So that's why the table becomes a bit tricky. So we're looking at C and E. So when you have this is a 0 and a 1, so this should give you a 1. This is a 1 and a 1. You get a 1. This is a 1 and a 0, you should get a 1. And this is a 1 and a 1, you should get a 0. When you have a 1 and a 1, you get a 0 and a 2. This is for a OR gate. Oh no, a OR gate, everything is 1 except a 0. Now it's 0. So that should be a 1 as well. So you see, tricky. So this is a 1. So this is basically the solution for this table here for 6 marks. So you get 1, 2, 3, 4, 5, 6. 6 columns, so you get a mark for each column. You have to get everything correct in each column to get a mark basically. And there's any solution here, right? Right. Part B, let's say figure 9 shows an arrangement for making an electromagnet. So you have the circuit diagram, the voltage is 12. This is a rheostat. It's used to control the current or manipulate, I should say manipulate the current in the circuit. You have a magnet, a core electromagnet here. That's the cylinder, and you have some coils of wires. You have a meter to measure the current, and you have a switch there. States a material which is suitable for the core of an electromagnet. In other words, what should this cylinder be made up of? What material? So I have the material should be soft iron core. In other words, soft iron, right? And you can get it in any textbook as well. Now, part two, so it just look complicated and not complicated. Part two, they say less two factors which would increase or which would cause an increase in the strength of an electromagnet. So two factors, since I just say less, I will just put it here. So the first one would be increase the current in the coil. That will cause an increase in the strength of the electromagnet if I increase the current. The other one would be to increase the number of turns or coils around the magnet, the number of turns in a coil. Right, so the number of turns. States how component X can be used to increase the strength of an electromagnet. Well, as I said, the rheostat is used to manipulate the current or to change the current in the circuit. So recall the formula from Ohm's law. V is equal to IR. We know an increase in current increases the strength of the magnet, right? So if you make I the subject of the formula, you're gonna get V all over R. So if you decrease the denominator, you're therefore increasing this value for I. So if you decrease the resistance, you're increasing the current. And if you increase the current, you're increasing the strength of the electromagnet. Very important to note. Right? So what I have for this one is to adjust the rheostat, so you will get a greater current and a lower resistance. So adjust X to reduce its resistance. This will increase the current in the coil. Right, so that is a important explanation there, and you could use the formula to come up with an explanation. If you adjust X to reduce the resistance, once you reduce the denominator, the current value therefore increases. And if the current value increases, the strength of the electromagnet increases. Understand this, right? Right. So the last part here now, they say when the switch is closed, the reading on the ammeter is 1.5 ampere. Calculate the resistance, which is R of the circuit. So looking back at the circuit here, we see the current is 1.5, right? So the reading here is 1.5 ampere. We have the voltage here, we have the current here. We want to find the resistance. So we use the formula V is equal to IR. So R will be equal to V divided by I. But we know that V is 12 and we know that I is 1.5. So R will therefore be equal to 12 divided by 1.5 is basically 8. This is 8 ohms. Right, so that is the resistance there. So you have a clear understanding of the solution for this question here now.